Hello, this is Dr. D, and let's talk a little bit about the historical development of our understanding of the atom. So let's go back in time to ancient Greece, the time of Aristotle, and how they thought matter was put together. They thought that there were four elements: air, water, fire, and earth, and that combining these in different proportions, you came up with all the material world that you saw around us. This is what natural philosophy was. It wasn't modern science. Natural philosophy was philosophers sitting around talking, thinking about, coming up with ideas and explanations. And whoever came up with the best sounding explanation must have the right answer. And so this sounded like the right answer. But how would they come up with something like this? What if you took a green log and threw it on a fire? You see the fire, of course. You see the sap coming out of the end. That's the water. The smoke rose up in the atmosphere, dissipated, so there's your air. And then the ashes at the end is your earth. And so by putting those in different proportions, you came up with this piece of wood. In different proportions, you come up with you or me, or a rock, or copper, or whatever. But these four elements were combined somehow in different proportions to make all the different substances that we have. So let's also look at somebody from ancient times. And this is Democritus, who lived 460 to 370 BC. This is what Democritus thought. He said that if you took a stone and continued to cut it into smaller and smaller pieces, then at some point there'd be a piece that would be so small you couldn't cut it anymore. It'd be indivisible. And so he called these smallest particles atomos, which is the Greek word for indivisible. And that's what we get our modern word atom from, of course. Aristotle folks didn't think so much of this idea, and they rejected this theory by Democritus. Moving ahead in time to the 1800s, this English gentleman by the name of John Dalton lived from 1766 to 1844, and he proposed his atomic theory. He said that atoms are made of extremely small particles called atoms, using Democritus's word. And we certainly agree with that. He said the atoms of a given element are identical. The atoms of different elements differ from one another. And we certainly agree with that second sentence, that copper atoms are different than cobalt atoms. With the understanding that we now have of chemistry, we know that atoms of a given element aren't all exactly identical. There's such things called isotopes. Yes, all atoms of copper have the same number of protons, but they have a different number of neutrons, and that gives rise to isotopes. He said that atoms cannot be subdivided, created, or destroyed. Law of conservation of matter comes into play here. The atoms can't be created or destroyed. But we do know that atoms can be subdivided. That there are some subatomic particles, and we'll be looking at those in just a moment. He said atoms of different elements combine in small, simple whole number ratios to form compounds. That's very true. H2O is water. H2O2 is hydrogen peroxide. And Dalton said that in chemical reactions, atoms are combined, separated, or rearranged. And so we can take that hydrogen peroxide we just mentioned, H2O2. With time, we can see it decompose into water and molecular oxygen. H2O2 forming H2O. Those atoms are rearranged into make new compounds. And so much of what Dalton subscribed to, we certainly believe today. So a few modifications, and that's what science is all about, the scientific method. New information comes along, and you have to modify your theory. So let's look at those subatomic particles. This is Sir Joseph John Thomson. another Englishman, who lived from 1856 to 1940, and his work resulted in him being awarded the Nobel Prize in Physics in 1906. What Thomson was able to do with the help of a cathode ray tube was to determine the charge-to-mass ratio of an electron. He determined the charge-to-mass ratio to be 1.76 on 10 times 10 to the 8th coulombs per gram. And he did this using something that's called a Crookes tube, or a cathode ray tube. Cathode ray is the stream of electrons. And we can see a picture of this in these three photos. The one on the left is a cathode ray tube, and you've evacuated it, taken all the air out, and you pass electric current through it, and you can't see the electrons, but you can see the glow off the phosphorus stream in each of these. In the middle photo, you can see a magnet, and it's deflecting the beam up. Turn the magnet around, and it deflects the beam down. And so he was able to determine the charge-to-mass ratio of an electron. That's J.J. Thomson. This is Robert Millikan. He lived from 1868 to 1953. He was an American. And he determined the charge of an electron by examining tiny oil droplets. And for this, he won the Nobel Prize in Physics in 1923. And what he was able to do was determine the charge, and that was to be minus 1.6022 times 10 to the minus 19th coulombs was the charge on an electron. So how did he do that? He used this device. It's a large chamber in which you can squirt some oil droplets using this atomizer. It would naturally fall down due to gravity. He had two plates in there, a positive plate and a negative plate. He used a microscope to see those droplets. And he had an X-ray source to put a charge on those droplets to ionize them. And so those droplets naturally would fall through this hole in that top plate, but by adjusting the voltage on those two plates, he could actually suspend them in midair. And you can see that through the microscope. By looking at the charges on those droplets, he saw that they were all multiples of a number, and they were multiples of this 1.6022 times 10 to the minus 19. So voila, there's your charge electron. And so Thomson gave us the mass to charge ratio. Now you know the charge, you can figure out the mass. And so the mass is 9.10 times 10 to the minus 28 grams. That was Robert Millikan. The next big development was the discovery of radioactivity by Wilhelm Röntgen, a German who lived from 1845 to 1923. And he also used Crookes tubes and discovered that when they hit a metal, that some other rays were being given off, some sort of unknown ray. And so since we often use X as the unknown in algebra, these rays were unknown, he called them X-rays, and the name stuck. Some people tried to call them Röntgen rays in his honor, but that never really took on. So for this, he won the Nobel Prize in Physics in 1901. And here you can see a picture of his wife's hand that was taken a few weeks after his discovery of X-rays. So Röntgen is not just the discoverer of X-rays, he's the father, in essence, of modern radiography, using X-rays in the clinical setting. This gentleman, a Frenchman, Antoine-Henri Becquerel, 1852 to 1908, discovered radioactivity, which is the spontaneous emission of radiation. For this, he won the Nobel Prize in 1903, where he shared the prize. More on that later. And so here's a picture of the results of his experiment. He had taken a photographic plate, put it in a dark drawer, and had some uranium ore in that drawer. Came back sometime later, developed the plate without it having been exposed to light, and saw that it had been exposed. So that ore had to be given off something, some sort of particles. And so he called that radioactivity. One of his co-workers who shared the Nobel Prize with him was, of course, Marie Curie, or Madame Curie. She won 2 Nobel Prizes, one in 1903 and for her work with the radioactivity in Becquerel, and the 1911 Nobel Prize in Chemistry for having discovered radium and polonium. Marie, along with Becquerel, shared that 1903 Nobel Prize in Physics with her husband, Pierre Curie. Pierre was killed in a tragic traffic accident, and so he wasn't around to help share with the chemistry prize that Marie would eventually win. It turns out they had a daughter named Irene, who married Frederick Joliot, and together they were awarded the Nobel Prize in Physics and Chemistry in 1935 in recognition of their synthesis of new radioactive elements. So that's the famous Curies. So what are the different types of radioactivity? If you took some radioactive material and put it in a lead block and had a hole, an orifice in it, so that's a way that some radiation could escape, and you pass it past some electrical plates, you can see some interesting phenomena take place. And the way we're going to detect them is by using some photographic plates. So some of the rays pass through untouched. They'll wind up being what we call gamma rays. Some of them are deflected toward the negative electrode, we'll call those alpha rays, and some of them are deflected toward the positive electrode, what we call those beta rays, or beta particles. So that alpha rays are helium nuclei. It's a helium atom that's lost its nucleus. Since it's lost its electrons, so all you have is the nucleus. So if you lost your electrons, you're now positive. So that's why those alpha rays or alpha particles are attracted toward the negative electrodes, since they have a positive charge. The beta particles are electrons. And so electrons, we know now, have a negative charge, hence they're attracted toward the positive plate. And since the gamma rays aren't attracted toward either, they must have a neutral charge. It turns out they're just another form of high-energy electromagnetic radiation, like X-rays, or UV visible, or infrared radiation. So those are the types of radioactivity. This is Ernest Rutherford from New Zealand. And he won the Nobel Prize in 1908 for coming up with what we will refer to as the nuclear model of the atom. His experiment was to take an emitter of alpha particles, shoot them in a piece of gold foil. And the expectation was that they would pass through the gold foil unimpeded. He found out that some of them, however, were deflected. And that some of them even were deflected back toward the radioactive source. He said that this was amazing, that he did not expect this result. That it was as if you shot a cannonball at a piece of tissue paper and a cannonball rebounded right back at you. Why in the world what was deflecting those alpha particles, those big helium nuclei back towards you? Must be the way the atom is arranged. And so Thomson had talked about a plum pudding model of the atom, where it has some sort of gooey stuff that had a positive charge to it, and in it were the electrons. That were like plums in a pudding or raisins in a pudding. So that was the plum pudding model. Well, that's why, using that model, Rutherford thought these alpha particles would just zoom right through this gold foil, but they were interacting with something. What were they interacting with? The nuclei, the nucleus of the atom. So he's the one who gave us the nuclear model of the atom. That's Ernest Rutherford. So we talked about electrons, we talked about protons. What's left? Neutrons. So this is James Chadwick, and he wound up getting a Nobel Prize in physics in 1935 for his work in discovering neutrons. And so what he did is he took a polonium source that's an alpha emitter. He had some paraffin wax, and he had a Geiger counter to count the radiation at the end. And so he was detecting these protons, this radiation at the end. Well, what was causing that? The alpha particles were striking this piece of beryllium, and the paraffin was what was giving off, or the wax, the solid wax, was giving off the protons. Well, how is that happening? There's got to be some sort of substance, material, that's transmitting that energy from the beryllium to the paraffin. And so those wound up having to be neutrons. They had to have an equivalent mass so that they would not have enough energy to knock those protons out of the paraffin. And he also determined they had to be neutral. And so protons and neutrons have a mass of about 1 AMU, atomic mass unit. Protons are positive, neutrons are negative. And so Chadwick is credited with the discovery of neutrons.